Welcome to Quantum Photonics. We have a recurring speaker, and today he will be speaking about a topic which is very interesting. And of course, the groundbreaking discovery of the Alena tensor, a remarkable class of energy momentum tensors that promises to revolutionize our understanding of physical system in both curved and flat spacetimes. This tensor offers a mathematical framework that elegantly bridges the descriptions of systems in these disparate space-time geometries, rendering them equivalent. As elucidated in previous publications, the Alena tensor exhibits remarkable versatility, and in curved spacetime, it faithfully reproduces venerable Einstein field equations, while in the flat Minkowski spacetime, it adeptly describes physical systems with configurable fields. This duality not only simplifies the formulation of quantum field theory equations, but also opens avenues for novel interpretation of the Schrödinger equation. So, of course, to speak about this is our guest speaker, author Dr. Peter Ogonowski. And I would like to say to tell you something about him. Dr. Ogonowski is an experienced researcher, manager, and lecturer. Manager with over 20 years of experience, lecturer, author of a series of lectures and trainings, researcher, author of publications in physics, and management, and in 2010 he was selected as one of the four experts consulting planned changes in the rules for co-financing physics and management. In 2010, he was selected as one of the four experts consulting planned changes in the rules for co-financing innovative projects from EU funds in Poland. In the years 2018 to 2022, he was a member of the expert group in auxiliary body at the Chancellery of the Prime Minister of Poland. He conducts classes for 1 to 2 degree students and for MBA students at the Kosminski University, University of Management and Banking, University of Logistics, University of Personnel Management, and the National School of Public Administration. So, without further ado, I would like to present to you our guest speaker, Dr. Peter Ogonowski. Peter, welcome to Quantum Photonics.
Hello, Cecile. Hello, everyone. Um, I'm very glad that I'm able to be here once again. I've heard that you liked my previous presentation, and there was a lot of questions. There are also some questions that was inspiring for me, and this is the reason why I asked for maybe another presentation. And you will see in a second that you influenced my work, and I think great things were discovered because of your questions. So you may feel part of all of this project that I'm managing now. Uh,
Peter,
yeah.
uh, sorry to interrupt you. Just go ahead with your presentation. You might be surprised that I might be out of the room because I think I should call the other Peter, the other Dr. Peter. I should go out and call him, but just go ahead. Because I should send him an invitation. So, yeah,
Okay.
please continue.
Okay.
Thank you.
Okay. Okay. Thank you. And I hope you may see a presentation because I asked Cecile to add presentation in such way that you will be able to take it and to, let's say, track what I'm saying about. So there are big numbers on the right upper corner of this presentation, and I will be referring to these numbers for you to be able to see what slide we are talking about. So let me start that there are some news about Alena Tensor. I know that at least some of you are really interested in the subject. So let me tell you a few words what have been discovered in the last, let's say it, 2 months. As I promised, there is only the matter of time because we are now able to calculate a lot of things which are really, really interesting from the, of course, from the perspective of physics, but also from the perspective probably of many of the regular non-physicists. But I will start from some, let's say it, how to say it, retrospection, some reminder. What is Alena Tensor? What we are talking about? Oh, maybe one more thing. I hope that I will be with the same energy. I hope that I will be with the same energy and the same enthusiasm that I was doing the speech last time. However, today I have to say that I've been driving for 6 hours. I've came to my home 20 minutes ago, no, 30 minutes ago. So I feel a little tired. So I hope you will excuse me that maybe I won't be so energetic than the last time, but maybe the content will be more interesting. Okay, so we'll start with the agenda. This is slide number 2. I'm going to say a few words about what the Alena Tensor is, for any case, because maybe some of you was not able to attend in the previous chat. Then I will say about new discoveries, because there is a lot of them. There are some discoveries about, for example, what the matter is, or I have been able to find a solution that explains if black holes may have singularity or no. This is a topic which is very popular on the popular science media. So I also have some resolution for this, some answer. We will see also why charged particles have spin, which is something that we all know about it, that charged particles are spinning. We didn't know what exactly is it, the spin. We didn't know how it's going to, how is it, how the spin is coming from, but it seems that now it may be explained. And then I will tell a few words about result in the quantum area, especially in the Schrödinger equation and Klein-Gordon equation. And I will finish with a few words about quantum gravity. And a short disclaimer at the beginning. Um, I'm going to tell you a lot about the recent discoveries from my and my partner Peter, and my fellow scientist, which we are working together on this over this article and over this solutions. But of course, before it will be reviewed and accepted for publication, we must say that this is, at that moment, this is just the result of calculations, but it have to be confirmed. So you're really first people that hear about it, and if it will be published, then I think it will be really big thing. So you may feel that you are on the very birth of the great idea and great findings. But of course, we need confirmation, we need review, and so on. So have some distance, because sometimes even with the best will of the researchers, something, for example, happened during the process that declines such findings. However, after checking calculation many times and writing this article, this newest article, I might say that it seems that it really works fine, and I have a good hope about the review process. So let's start. Let's start from what Alena Tensor is. This is slide number 3. And for people who didn't hear about it, Alena tensor is some mathematical construction which allow us to do things that were impossible before, and it joins different descriptions that we use in physics. This is not just about quantum gravity. Of course, quantum gravity is part of it, but this is much more. Alena tensor allows to make some smooth transformation, mathematical transformation, from curved spacetime to flat spacetime with fields. It also gives some mathematical framework to analyze fields in the classical way, relativistic fields in the classical way, but also using Lagrangian Hamiltonian mechanics, we are able to switch into quantum description, which means this is not only about quantum gravity, this is about quantum, any quantum interaction. And what more, it also gives some clues about the cosmological problems. We are, for years, we are thinking, we are searching for the solution, what the dark energy is, what the dark matter is, and so on. So there are also some solutions coming from this usage of Alena tensor that shed new light on the problem of dark matter and dark energy, for example, which means we gave some explanation of what is dark matter or what is dark energy, and also it enables us to use some, let's say, mathematical model also for such problems like the beginning of the universe, Big Bang, and so on. So this is not only about modeling movement of planets or whatever. It's much bigger tool. And Alena tensor also agrees with thermodynamics and gives some clues about thermodynamical problems that we use in physics. And to be honest, most of these areas are now separated. Of course, we are able to make some bridges between them, but it's hard to say that these areas are really connected. We have let's say it's broken links between these theories, and the most famous, of course, is quantum gravity, which is the link between gravitation as we understand it now in the general relativity and quantum description of gravity, when we don't know how to make this description. So Alena tensor also show some um, gives some explanation what exactly this quantum gravity may be, and why we were not able to see this gravity in quantum equations. So this is very briefly what is Alena tensor about. And on the slide number 4, you may see what possibilities Alena tensor open. And this is quite long list. This is a long list on 2 slides. The most important are description of motion in curved spacetime and its description in flat Minkowski spacetime appears equivalent, which means that we are able to switch between them using some transformation in which field is related to the spacetime curvature. Then, according to this method, there are no inertial systems. According to this method, spacetime is just a way of perceiving the field, which is quite big, let's say, quite big. How to say it? Uh, mm, uh, just a second. Okay, I find the word. Quite big idea. This is a conclusion. I needed a word. Conclusion is quite big conclusion. Because we are mainly thinking about the space-time as some scenery when some physical phenomena are taking place. But this approach shows us that spacetime is indeed a way of perceiving the field. Let me stress it. It means that everything around you is just wavering field, and it's not something stable. It's just a field, but we perceive it as something stable. Alena Tensor also allows us for the analysis of the system in the quantum approach, and gives some bridges to not only quantum field theory, like quantum electrodynamics or electroweak interactions and so on, but also gives some clues about classical quantum mechanics. And I will also refer to it in the next slides. Then on the slide 5, you have the next possibilities that Alena Tensor opens. It has the potential to explain what cosmological constant is. This is also quite important thing because cosmological constant is, kind of, let's say it, a cut from the Alice from Wonderland, because it appears in the equations and then it disappears depending on what we are calculating, and nobody knows. Even Einstein didn't know if it was a good idea to have this cosmological constant. So it seems that it's needed, and Alena Tensor also brings some explanation why this constant has to be part of the equation and what exactly it is. Then it also gives some correction to Einstein tensor, proposes some correction to Einstein tensor, because maybe some of you which are really interested in quantum gravity or general relativity knows that Einstein tensor is at the moment is related strictly to gravity. I mean, we understand it as some kind of description of the gravity, and curved spacetime is just the way we perceive gravity. So from Allen tensor, we have a bit different explanation, because we show that, of course, this is gravity, but plus some additional force, which may be neglected for some applications, but in general, it's not just gravity. There's something else. Let's call this other force or additional force, and this additional force has the potential to solve the mystery of dark matter. And I will also refer to this additional force in the next two slides, because it was one of the most um, the biggest enigma in all of this idea of Alena tensor. Also for me, I was trying to find explanation what is this force, and now we know what is this force and what it describes. What is also interesting, um, from this Alena tensor equations, gravity in the system arises naturally. So any field in the system, if we consider electromagnetic field or electroweak field or what any other field, then gravity just pops up from the box. And this is not the force that we need to add in some artificial way. It's just something that just appears, that it has to be if there is any kind of field in the system giving some physical object which is called stress energy tensor for the field. So if there is any stress energy tensor for the field, then it must be gravity. And gravity turns out to be indeed some specific force. It appears that it's not interaction between bodies, but it appears from the bending of the direction of the field energy transport by the energy density gradient, which is exactly what we should expect uh, if you would like to describe gravity in the flat spacetime using approach from general relativity, which means that this is not the Newtonian description. This is not just interaction between two massive bodies. This is indeed something which is equivalent of curving spacetime, but when we analyze it in the flat spacetime, it appears that it just curve the light path, and all goes, let's say, all other things just follows, and much more, because there is much more about Alena Tensor. I'm not going to tell too much about the main concept. You, by the way, you may find a lot of information on the internet at the moment, but I will focus on the new findings. And let me start from something at the beginning that I hope you will like. That um, it's the reason for this meeting. You asked me really wise questions uh, during our last podcast. There were some questions that I answered, but then I was thinking about them for, let's say, many hours. Especially two questions that was given during this podcast, and it really intrigued me. If am I right with my answer? Maybe I should check something. Maybe I should calculate something. And really, two of these questions uh, forced me to discover really interesting things. So you may really feel that you influenced the research process. And indeed, some of these findings comes exactly from your questions, from me trying to answer your questions and thinking about them. But I will focus. I will, of course, I will focus this answers. But let me start from additional force in the system. I was thinking a lot about what is this additional force that pops up, because um, if you try to describe the system with electromagnetism, when we consider only electromagnetism as a field, then we get, in Alena tensor, we get electromagnetic force, we get gravity, and we get some additional other force. And I wasn't able to understand what kind of force is this and what is the source of this force. So I was searching for it, of course, with help of Peter. And finally, it appeared that um, this other force is something that we already knew. There is some force which is let's say not commonly known, but it exists and it's quite well described. This force is called Abraham Lorentz force, and maybe easier name also sometimes used for this force is this force is also called radiation reaction force. This is some kind of force that comes from following phenomena. Uh, if there is an object which is, for example, accelerating because of electromagnetic force, then it cannot accelerate just in infinity. I mean, it cannot be faster and faster and faster, because in the system, if something adds energy, then this energy has to comes from. So this force says that system at some point must limit this acceleration, and it reacts. This is why this is called radiation reaction force. And interestingly, it appears that this force other, this is exactly Abraham Lorentz force, or very, let's say it on the very specific um, way of description, because uh, this force exists, but from the very beginning. But this is very small force, and from this equations comes out that we may see existence of this force mainly on two scales: on very small scale, which is quantum scale, and on very large scale when we have big systems with very high energies. So then we will be able to notice this force. And since in curved spacetime, as described by Alena tensor, the Einstein curvature tensor is related to gravity and this other force, it would mean that uh, that interaction currently attributed to dark matter can be explained, at least partially, as a result of omitting this force, this other force, in currently used equations. I mean, when I calculated, then it suddenly it appeared that okay, this is obvious. We indeed don't have such kind of force in the general relativity. We don't see it, but it should be. It should be because this is some kind of, let's say it, expected force coming from conservation of energy. So this is really intriguing because suddenly it appears that this tensor, let's say it was wiser than me. I mean, from this tensor, this Alena tensor comes out some force that I was not able to understand. Even I know that we should expect such force, but you don't remember everything. Even if you have learned a lot about physics, then sometimes it surprises you that it appears there is a force which is really expected, but you forgot about it. So this is really interesting. I would say intriguing discovery, because maybe indeed part of this, maybe not all, the whole. We don't know exactly what dark matter is. Maybe there is something more than just the effects of this force, but at least part of this dark matter phenomenon should be indeed be able to be explained based on this force. But what is more interesting, uh, because of this force existence, uh, we shouldn't expect any phenomena which is against, let's say it, which is against physics, which is not physical. So we have understood that it prevents from some non-physical effects, and the great example of this effect is singularity. There is a lot of information about black hole singularities. There is a lot of information about what singularity may be, how it may work. Maybe there is some, bridges to other worlds, like Einstein-Rosen bridges, something that we called wormholes, and so on. So, it seems that using this description that we use, we get a physical system which prevents from existence of non-physical solutions like singularity. So from the perspective of Alena tensor, we shouldn't expect singularity, and because we don't use cosmological constant, we don't use some this description, including this additional force, then maybe we get something like this in equations now uh, on general relativity uh, issues. However, from this approach that we use in Alena tensor, it turns out that we shouldn't expect some such phenomena. So this previously mentioned other force, in some way safeguards the principle of conservation of energy. And thanks to its existence in the equations, just non-physical effects disappear. And it also applies to black hole singularities. By the way, there was recently a very famous article by Roy Kerr, which put in question singularities. I also wrote this article. There was a lot of information in the public media about this article. So it turns out that we just get exactly the same result. I mean, we shouldn't expect singularities in black holes. Okay, so let's switch to something closer to the to life, because black holes are far away, and let's hope that we are not going to meet any of such black holes in the future. Let's concentrate on something which is closer, and I'm going to say a few words about matter, at least charged matter. So it turns out, now we are discussing the slide 8. It turns out that energy density of electromagnetic field in the system may be expressed not only in the classical way, because there is some classical description what this electromagnetic energy is, but also it may be expressed as electric energy density of particles and energy density related to their magnetic moments. I don't know if you are familiar with electromagnetism. It will be hard to explain it without at least basic knowledge, but I try to do it. I mean, we have some description for electromagnetic field at the moment that we use, and we know that it works. And from this Alena tensor comes out that electromagnetic field may be perceived also in a bit different way. It doesn't mean that it is something else. No, we still are talking about the same electromagnetic field, but we may also make some division into part of this energy coming from, let's say it's electric energy and magnetic moments. Why this is important? Because we know from quantum mechanics, by the way, we know that um, we should expect magnetic moments in particles. So if we get description which naturally uh, consists the magnetic moments, then there should be some link to magnetic moments of particles, something that we use name spin. We call it spin, but indeed the spin is about magnetic moments. So it appears that that's true. We have calculated that it's possible to split the stress energy tensor for electromagnetic field, which means some object which describes the field, into two components. Part of this component is describing density of charged matter in the system, and since it describes polarization and magnetization, which is in electromagnetic field, it was called by us polarization magnetization energy momentum tensor. And also we get second part, which is called electric displacement energy momentum tensor. And it appears that it describes the transfer of electromagnetic field. And why I'm so excited about it, because this is exactly the way that we perceive matter in quantum electrodynamics. This is exactly the image that we have in quantum electrodynamics, because in such description, leptons exchange photons. So we got exactly the same result. Then we have part of the system which is energy density of charged matter in the system, and this is part of this stress energy tensor, polarization magnetization. And we have something which is responsible for the transfer of the energy, electromagnetic field energy. So this is exactly the same description, but classical. We only have at that moment, up to this moment, we have only quantum electrodynamics which sees the system in this way, when you have leptons and the leptons exchange photons. So we have equivalence of this description in the classical let's say it approach. So, okay, can you hear me, by the way?
Yes,
Okay,
yes, I can hear you.
okay. You are so silent that I didn't know if you still hear me. So, what is more interesting, when we use this description that I mentioned, that the electromagnetic stress energy tensor is split into parts responsible for matter and part responsible for energy transfer, then suddenly gravity evaporates from equations. I mean, suddenly it appears that gravity is absorbed in the description of matter. So, and it explains that we hope that it explains, because let me remind you that we need review, but this is some kind of result which is really interesting, because with such description, only electromagnetic force is visible in equations. Suddenly gravitational force, just, you cannot see it when you calculate the Lagrangian and effects of this, of usage of this Lagrangian. So it would explain. I don't say now it explains, but it's too fast. But if it will be confirmed, then it explains that gravity is indeed part of quantum electrodynamics. Let me stress it because it's really big. Everyone is looking for quantum gravity as some additional interaction. I mean, we have quantum electrodynamics, we have electroweak, we have quantum chromodynamics, and we are looking for gravity. So if we are right with Peter, then gravity is already in these equations, but we cannot see it. We cannot see it because we use some description which is based on Dirac approach. It's based on some spinor matrices. And if we use such spinor matrices, then gravity is already in this description and we cannot see this force. So there is quantum gravity already as a part of existing quantum mechanics. It would be absolutely, mind-blowing if we are right, because it would mean that we don't need to look for this force anymore, because gravity is already there, but it was hidden in the description of matter that we use since Dirac introduced his approach. So in we could say in some way we have this way we would really find quantum gravity, but not as a solution that everyone expects, because everyone expects that gravity will be just something very similar to existing quantum electrodynamics or quantum chromodynamics. It would mean that gravity was all the time there in their equations. We just missed it because we have used different approach to describe matter used by Dirac. So it would be huge. I hope we are right. But let's go further. What more comes out from this description of matter? You know, in this obtained description of charged elementary particles or matter, it comes out that elementary particles just should have some properties, and we have found two properties which are very important, and moreover, they're indeed new that they are true. First property is that charged particles cannot exist at complete rest. And this is something that comes out from equation, because if they would be in rest, then suddenly all the equation just goes to zero, and there is, there is no interaction, there is no electromagnetism, and so on. So particle cannot be in just complete rest. And this is true, because every particle is still, in move. It's vibrating or spinning or whatever. We know from quantum mechanics that there is nothing like just complete rest. And the second conclusion that we got from equations is that, and just, I hope you are sitting, that the primary source of electric field of particles is magnetization, magnetic moment. And this is exactly what we all think that it's true. I mean, we don't have a proof for it at that moment. We just know that it should be like this. But we don't know why, and so on. So it comes out from this equation that indeed, in the Alena tensor description, the primary source of the electric field of particles is magnetization, magnetic moments. And without these magnetic moments, there would be no charge. So, so this is also very, very interesting, because we don't. How to say, it's not invented, it's not postulated, it's not kind of let's say it's something introduced to equations. It's something what comes out from the description. And this is very, very valuable because it means that it's not artificial. It's just part of the whole system. Okay, what more? What's more interesting? We also got some, let's say it's additional results related to quantum equations. And it will be the hardest part of the presentation. I hope you at least know anything about quantum mechanics. I'll try to say it as simple words as I can. This is slide number 10. So you may see the equation which is on the slide. And let me start from explaining something. We don't have one quantum description. We have many. For example, we use something which is called Schrödinger equation, which, by the way, was first description that was discovered. But we know that Schrödinger equation is just approximation. We knew it. So we were looking for, I mean, in physics, we know. So all physicists were looking for some different descriptions, and there are many different. The most famous are Klein-Gordon, which is a Klein-Gordon equation. We know that how to use it. We know how it was calculated, and this is not very famous equation, but it exists, and it's used from time to time. And we have Dirac description, which is the most famous, and probably we could say that this is the most uh, complex, and but at the same time it gives the best results. So the most popular is at that moment Dirac approach. So what we have, what we get as a result in Alena tensor calculation for quantum mechanics. At first, we get something that looks very similar to Klein-Gordon. I mean, very similar because there is some difference in the equation, and this is relative magnetic permeability. And it appears that from Alena tensor, we have a solution that shows that Klein-Gordon equation, really famous equation, is some approximation of the system with electromagnetism, but it shouldn't give correct results because of this coefficient called relative magnetic permeability. And this result, if true, it may help explain the differences between Dirac description and results obtained from Klein-Gordon equation. And moreover, this is first quantitative result that may be used to prove or disapprove or falsify Alena tensor. So we have some really quantitative result that, if it will be used and gives the correct results for example, I don't know, atoms or some quantum applications, then it can ultimately falsify or confirm the Alena tensor theory. So this is really milestone. I think this is something that, if proven, it will say, okay, Alena tensor gives correct results, and it's probably it's working. So we may agree that it's true, but this is not all. When I calculated, because this is exactly part of my work, of course, we cooperate with Piotr, and Piotr is also part of it. But when I calculated, I've noticed that the same equation may be, let's say, transformed to some different different gauge of electromagnetic for potential. I don't know how to say it more simple. We different some gauges of electromagnetic for potential, so we may use different shapes of electromagnetic for potential, let's say it. So if we will use some different electromagnetic for potential, then we get something which is indeed, uh, uh, Schrödinger equation, but not in this approximated form, but in the form which seems more general. You may see it on the slide number 11. And you may see on the slide 11 that you have exactly Schrödinger equation, but with some small change, because in Schrödinger equation um, in the denominator we have two masses, 2m. Okay, we have mass multiplied by gamma plus 1 divided by gamma, which in for with the velocity, particle velocity up to 0.4 of the light velocity, it's about 2. It's very close to 2. And really, the big differences starts from this velocity 0.4 light speed. Yeah, so it seems that we get Schrödinger equation, and Schrödinger equation, we know that it works. It's kind of approximation, but I don't know if you're familiar with the way that Schrödinger comes out. He discovered this equation. To be honest, we don't really know why it works. We widely accepted because we know that it works. It drives to correct results. But the reasoning that he used to derive it was, let's say, it's quite non-formal, I would say. Okay, so we've got in the very formal way, as a result of calculation, as a result of some idea, which is quantitative idea, it gives us exactly the same solution that Schrödinger discovered, with small, of course, small difference, which is, by the way, expected, because we know that Schrödinger equation is just approximation. And we've got something which looks exactly like Schrödinger equation, with small difference, which may be approximated into Schrödinger result, but should work for the whole range of particle velocities. And this is the second equation which may be tested. This is the second equation that, if it's true, then we should be able to confirm it by calculating quantum systems. So I'm in progress with this now, not only me. I have also some information that at least one group of researchers is doing exactly the same, which means they are trying to falsify or confirm it. So this is not only our work, but if it works and if we will get correct results, that will be one more confirmation that the Alena tensor is the right theory describing our world. So this is the I would say these two things are the most, from my perspective, are the most groundbreaking, because we would get, let me say it once again, we would get explanation why Schrödinger equation work. We would get explanation of the Klein-Gordon equation with some correction, showing that we shouldn't expect the correct result from Klein-Gordon. And this is, by the way, true, because Klein-Gordon gives some, it may be considered as some approximation, but it doesn't give such accurate results like Dirac approach. So it also seems right, and it may be tested quite easy, may be tested in quantum systems, and we may expect quite soon, I hope it will be maybe a few months, some publications that confirm or deny Alena tensor. So it will be, or maybe, I don't know, maybe they add something to this idea, to this theory, because maybe we have, for example, missed something or whatever, but it's possible to test it and confirm it to be sure that it works or not. Okay, and at the end, I would say a few words about quantum gravity, and this is not quantitative. This is something which comes out from equations, but uh, this is not so easy to confirm, and I am still in progress in calculation. So please have some distance to what I'm saying now, because uh, we were all the time during this podcast, we were talking about electromagnetic system with electromagnetism. So we are calculating some system when we have electromagnetic field. But of course, we may, using Alena tensor, we may extend this description, this Alena tensor, into, for example, electroweak interactions. So when we look at only electromagnetism, um, we see that there is electromagnetic force, there is Abraham-Lorentz force, this other force, and we have gravity, Abraham-Lorentz, and electromagnetic. Gravity doesn't appear in quantum equations because of the spinor-based description of the particles that we use, and so on. And in this quantum electrodynamics, gravity indeed is, we may say, bending the path of light. But bending the path of light on the quantum scale is bending the path of photons, because this is a boson of this field. So on this quantum level, gravity is indeed bending of path of bosons. But this is only quantum electrodynamics. What happened when you extend Alena tensor to electroweak interactions? So it appears that then we get some additional term in the equation, and gravity is not only bending the path of light. All of you know that gravity is just, curving spacetime or just bending the path of light. So it appears that gravity for other interactions is just bends the path of all bosons of all fields that we consider. So this is not only bending the photons, this is bending all of bosons, okay, of all fields. So with such description, it seems, and let me stress it, it only seems, because I haven't finished my calculations, so I don't take responsibility for it. This is only just some, hint that comes out from equations, that this description would lead to need for redefinition of the strong force, because maybe let me say it once again. Maybe it seems that it looks like this, but maybe the strong force has much more to do with gravity than we previously thought. Maybe, okay, it's very probable that we will get solution in which strong force is not exactly the same force that we were thinking about. Maybe it works a bit different, that it's now described, and this is new approach showing that maybe it has more to do with gravity than with regular interaction. Because indeed there is some part of the equation that shows that we should be expecting um, bending this path of all bosons in this way, bosons of electromagnetic field, photons, and but also bosons of electroweak interaction, if we switch into electroweak description. So it opens some new area, and maybe there will be much more to discover. We will see. Now we've decided to stop making another discoveries, because there is too much of them, and we wait for approval of our article. We hope that we will get this soon. But now we will finish. We want to finish this step. We want to get confirmation or falsification of the results, and then we will go a step further. But I already know that at least 3 groups of researchers are checking this result. So we will see. Maybe we will get this information sooner than later. Okay, what's next, and what's worth to do in the next step? Um, of course, this is still the same list that was on this our last podcast. It's still good idea to continue describing subsequent fields and their relationships with gravity in the classical quantum and curvilinear approach. There is still good idea to recalculate known phenomena as like, for example, Hawking radiation or Unruh effect, which is it's possible now to describe this effects in a bit different way and maybe confirm or perfect existing solutions. There is of course still worth to research on dark matter, because Alena tensor, of course, shows some explanation, at least partially, for dark matter, but it doesn't mean that it has to be, all. Maybe there is something more to be discussed. Maybe there are some other solution. For example, we have at that moment some articles about sigma 8 tension, which would suggest that maybe this is this we should consider existence of axions. So there is still place to discover something about dark matter. This is not ultimate explanation, so don't expect that Alena tensor gives the whole solution. Probably, most of great discoveries comes not from one man or two men, even two Peters, but from the work of the whole society. So this is not work for two people. This is probably work for years for many people and whole this the society of physicists. So there is much more to discover than we do. Also, research on dark energy is a good idea because if we accept that Alena tensor gives a solution for cosmological constant, that this is indeed field invariant, it's not the end, it's just the beginning, because for example we may try to measure, to confirm it, or to deny it uh, for some fields and so on. So there is still a lot of things to discover in this area. And of course, the last but not least is development of relativistic continuum mechanics, because we get some equations that may be used in relativistic continuum mechanics, as I mentioned last time during the last podcast. Uh, this is still a great idea to develop it. And now I will make some step back and remind you that two of the discoveries was coming from your questions. So first discovery was related to this force, and uh, and this is why it forced me. Your question forced me to to look explanation for this force. But the second was, there was a question about what is quantum function, and if Alena tensor gives some explanation for the Copenhagen interpretation of quantum mechanics. So it seems that this explanation is right. I mean, it seems, because we've got exactly the same solutions that we should expect in quantum mechanics, like the Schrödinger-like equation or Klein-Gordon-like equation. And what is more interesting, I was really, uh, really curious how, based on Alena tensor approach, we are able to confirm or deny this Copenhagen interpretation. And the question is still open. I mean, it's still open place for discussion. But it seems that we've got exactly something that was expected, because with this Schrödinger like equation that we've got, uh, the solution shows that it indeed describes the wave function describing a photon associated with the particle. and changes in motion of a particle are related to the momentum of that photon uh, by some equations, by canonical for momentum and Lagrange equations. So it would drive to explanation that indeed this this uh, uh, this quantum wave function indeed describes some wave of, let's say it, electromagnetic wave, but this is not, this is not the way you think that this is only one photon, because it appears that we may use very different waves or group of waves, and this equation still works. So we can only expect probabilistic solutions, not exact solution from this equation. This is exactly how quantum mechanics explains the world today. So it seems that uh, somehow, okay, we are very, very on the same page that current knowledge in quantum mechanics, with some additional, of course, value, because we have calculated better, we hope better versions of equations. I mean, better Schrodinger, better Klein Gordon. This is probably, we hope that it's more close to reality, but it's still exactly this explanation that we now use in quantum mechanics. So the answer for your question now is, okay, we add something to the game, but it seems that indeed this Copenhagen interpretation is correct. Okay, and I will finish. I hope this is a lot of interesting stuff, at least for me. I don't know. I hope you are not bored, and you were interested. I hope there is anyone left on this podcast. So maybe you've got some questions. Maybe you would like to add add something, add some comments. And I'm really open for questions, because as you may see, your questions make me work harder.
Yeah, thank you, Peter. So, we are now opening the floor for anyone who would like to ask questions relevant to the topic. And I would just like to inform everyone that Peter is here. Peter Ogonowski is here as a recurrent speaker. And earlier we were not able to welcome the other Peter who is now on stage, Peter Skinzer.
Skinder.
Kinder. Yeah, welcome to Quantum Photonics. So, yeah, as I said earlier, we are welcoming people who would like to come up on stage and ask some questions relevant to the topic. And yeah, initially, Peter, I would just like to ask you, you mentioned earlier that there was another group trying to test this, trying to work on the Schrodinger equation, and
Mhm,
there to try to confirm
mhm.
or try to dissent from it. So, are these people also using the Alena tensor?
Um, I'm in contact with a few people, of course, from the society, with physicists, and I know at least about two groups that are trying to confirm or deny it. So confirm the result. Alena Tensor is quite new, and it's not easy to be learned, to be honest. So I don't know on which level they are, these groups, but I know that they are trying to confirm or deny the results. So if you have an equation coming from Alena tensor, like this Schrodinger like equation, you don't have to understand the whole Alena tensor to check if this equation is correct. So I expect that they are at that moment on the stage of trying to confirm it or deny or falsify it, just using the regular equation, and probably they have some knowledge about the Alena tensor, big enough to use it. So you know I don't expect that people will learn the whole theory without some confirmation, because this is kind of investment. I mean, investment. We invest our time. You also don't want to learn something which is unconfirmed and maybe disappear in the next 2 months. Of course, I'm like an author. I'm convinced that it's not going to disappear, because we get more and more and more interesting stuff. Just like I said last time, that it's only the matter of time that we spend on calculations, because it gives you um, many new interesting results all the time. So I suppose that it finally it will be, maybe with some changes, but it will be part of physics. But if this two equations will be confirmed in quantum applications, then we will know that exactly the solution that comes out from Alena tensor works fine. So I suppose they got knowledge big enough to use it, I would say.
Yeah, yeah, thank you, Peter. So I would just like to ask you if we bring this conversation to a bigger forum, for example, even on my Facebook page, for instance, which have a lot of followers, and especially there are a lot of physicists on
Mhm,
my group or those who are following me.
mhm.
Would you and Peter also be willing to bring this to another forum? Because there are a lot of um, just in this forum that we have now, when I posted our poster about this, there has been a lot of curiosity about Alena Tensor because, of
Mhm.
course, during the first guesting that you had here, many people were not able to see this, but yeah, there
Yeah,
has
feel
been
free.
a lot of
Yeah, yeah.
reaction about Alena Tensor.
Cecile, feel free to share this presentation. If you may, I can send you even bigger presentation for more technical audience. So I can just send you additional presentation with some numbers and some math. And if you, of course, if you would like to share it, because as many people will engage and test it, I think it's better for the theory and for physics, because it looks really promising. And this is not only my opinion, this is opinion of many physicists that writes to me. So I think it's good idea to share it on the bigger forum, which are also professionals, and just propose them to deny it or confirm it. I think it's good idea.
Yeah, because I thought maybe that in case the next time that we have this kind of discussion, we can invite people really in the physics field to join us on the panel to
Mhm,
listen to your presentation and ask questions, just like what you do when you have these conventions or
mhm.
presentations, so that it's a good field maybe to try to explore more and try to dissect your theory.
Okay, so of course I'm open for it. However, it will be a bit different presentation, because if we speak to professionals, then of course we may use more sophisticated names and objects, mathematical objects. So it will be a bit different kind of speech. Yeah, but great. I'm open for it.
Yeah, yeah, I will try to organize that if we can do so. I would like to also invite people from Perimeter Institute and also people who are very who are doing serious study on quantum gravity. So
Right.
I think this is very helpful because who knows, when you have science, it begins with the kind of question that you are trying to address, and the question is sometimes of course, most of the time, more important than the actual answer because science always is a continuing thing. So that would be very interesting.
Mhm.
Yes, so I think we had people who raised their hand, and I don't know why we could not bring them up here on stage. Yeah, I think there's a glitch. So Kevin is here. Yeah, Kevin is now on stage. And yeah, other people, it's, I don't know, I could not bring them up on stage. Maybe I'll try again later. So, Kevin, welcome to the stage.
Hi. Hi. Nice to talk to you again. I guess I'll just ask the obvious question. W- did my question of ultramagnetism spark any of this? If
Yeah, your question about electromagnetism, you asked the last time. You know, all of these questions were very interesting, and all of these questions sparked some ideas in my mind. So you may feel part of this researching process. Asking why questions is also very important in this research process. So for sure, it was something that was I was thinking about. I would have noted all of the questions, not only yours, and some of these questions really, you know, made me think hard about the how to answer this in more technical way. So I just started to calculate, and sometimes I had to change perspective. So yes, your question about electromagnetism also was part of this, let's say it, research process.
Yeah, and it helps me. It helps everyone too. Like because it made me look it up more. Like like ultramagnetism has Fermi surfaces. That metals that exhibit distinct spin polarization, and I have a good friend at the Fermi lab. So now I'm gonna try to contact him and see if try to get some more information about all this D wave. All the wave vector space.
Hmm.
Breaking time reversal symmetry. Yeah, I'm learning a lot too.
Okay.
Yeah, Kevin, I would like to comment about altermagnetism. We really would like to bring the people who presented the paper here, but there is no response. So I think they are in the best position to make a comment on that because a lot of people haven't heard of that yet, and it is not yet widely accepted or popular in the academic field. So a lot of people, I think almost all, haven't heard of it. Maybe it's only you and me, and maybe a few other people. So yeah, I hope they can come so that we can check what they have.
Okay. Okay.
So
Any other?
yeah, I would just like to reset the room at this point. We are here trying to listen to the presentation of Peter and Peter about Alena Tensor's possible applications in the unification theories. So in the past, Peter was also a speaker in trying to straighten curved space-time using Alena Tensor. And Peter, for those who just came in, can you tell us a little bit about Alena Tensor? Because, yeah, even in our posting of your poster, which got a lot of impressions in social media, especially in my circles, they were asking, uh, what is Alena Tensor possibly? So can you just give a brief overview to those who came in? I know that you already did in your initial presentation, and I
Mhm.
would like to refer you to that for those who just came in. Please go to the profile of Peter, and underneath his profile there is a recording, a playback of his presentation of the Alena Tensor. So, but very shortly, Peter, if you would like to, yeah, accommodate us about Alena
Mhm.
Tensor.
Okay, in simplest word, I would say that Alena tensor is some mathematical objects that allows you to manipulate fields, space and time. And we are able to look at the whole space-time or part of the space-time with field or without a field in curved way or in flat space-time. So you are able to use it like kind of parameter changing the perspective you want to use. So this is very elastic tool. This is not ultimate theory. I suppose there is a lot of to discover, but this is a really useful tool to make research related to such phenomena like space-time, matter, field, okay, and take a look at this phenomena from different perspectives. And moreover, since this is mathematical objects, it allows you to generate some solutions of the systems. And I presented to you today some solutions that comes out from usage of this tensor. It's not easy to use. You need some time to learn it. You need some time to understand it, and you need a bit different perspective that we use in physics now, because it's based on some assumptions that you have to accept. Like, for example, that field is not something added to stay space-time, but this is just part of the system. And if you use it, you are able to generate some properties of the system, like properties I've already described, like that we cannot have singularities, that we have some forces, and we are able to describe these forces, like spinning particles, like source of electromagnetism, like quantum equations describing the system. So it's kind of a root, like you have a root in the tree. You are able to expand this root and take a look what comes from these equations uh, going through how, how to how to say it, branches, going through branches up to the leaves. So very small solutions. So we are able to describe the system in completely new way, which was not possible previously.
Thank you. So right now I'm just inviting Eagle Hawk, who has some comments here at the room chat. I'm inviting him to speak on stage so that he can interact. But I wonder if he's able to speak. And I would like to clarify that we are discussing theories and physics concepts here based on the tool of the Alena tensor. So uh, bear in mind that in case you hear answers or had already heard comments here, that was our only basis, and we are not discussing a physics concept or a phenomena, um, we not uh, outside the parameter, but basically while using the Alena tensor. However, your comments are very much welcome. So I would like to ask Bob at this point if he is able to read the comments of Eagle Hawk on the room chat.
Sure. Uh, Doctor, do you have any thoughts on the Townsend-Brown equation being used now in new work related to warp drives and the work of Professor Alcubierre in Mexico involving anti-gravity?
Okay, a very interesting question. Thank you. You know, um, I didn't. I honestly, I didn't go through this branch onto this to this part of this whole tree, because this is indeed a really huge tree of solutions. But I may say something which is also for me interesting. I know the work of Professor Alcubierre, and I know the idea of wrap drives and so on. Some part of this idea is based of approach that we are able to manipulate the space-time curvature, we are able to move, let's say, without need for acceleration, because we just manipulate curvature of the space-time, which from the mathematical point of view, if you solve the equations, Einstein equations, it seems possible. At least we need something which is quite exotic, and we need something which is called negative energy. I have read few articles about it. I was even corresponding with one of team members in NASA, which is working in the project which is related to this idea. And it seems that Alena tensor maybe not even solve any problem there, but it gives some potential solution. And let me explain what kind of solution it is. Alena tensor shows that we are able to manipulate space-time curvature by manipulating field, because in the Alena tensor approach, um, space-time curvature is related to the field. So it's possible to imagine that by manipulating the field, which are able to do it, because we know how, for example, how to manipulate electromagnetic field. So it's possible to imagine that we are able to interact, maybe change the space-time curvature using some manipulation of the field. And this is something new. This is something what Alena tensor add to the game, because the only way we knew how to manipulate the field is using present knowledge based on general relativity, is by existence or non-existence of mass or energy, we would say. So Alena tensor gives something more, shows that the tensor of the field is responsible for the metric tensor describing the curvature of spacetime. So it's theoretically it's possible to shape the field in such a way that we would need. I say theoretically. So maybe it could add something to the game. And in the newest article, I even have a small paragraph about it. I added maybe 3 sentences about it. That using this tool, maybe some new areas open for manipulating spacetime with this field tensor, which could help, maybe potentially, maybe could help in works related to Professor Alcubierre idea. So there is some potential. I didn't calculate it. I didn't dive into it because there is too many things. We have to concentrate on something. I think we have calculated a lot and already found a lot of phenomena. But from my perspective, the phenomena we were discussing during this podcast were, let's say, it more important, like for example quantum equations that describe quantum systems, because it gives you great tool for any kind of calculations. And if it will be confirmed, that it opens just universe of solutions. But um, uh, let's say it, ways of usage of using Alena tensor maybe also work over this Professor Alcubierre idea. So yes, I confirm that it's for sure it's worth to check how it corresponds to calculation made by the Professor Alcubierre and followers, because there is more articles about it. I have read at least 3, so and I know that there are many more. So I just decided that maybe I will leave it for some other day.
I
Yeah,
wanted to
thank
say
you, Peter.
I
Uh,
wanted to say thank you on behalf of Eagle Hawk, who put a comment in the chat. Thank you.
Thank you.
yeah, thank you, Bob. I would just like to tell the audience Avi Love of Harvard spoke about the Alcubierre Drive when he was our guest speaker here. Unfortunately, there was no recording which appeared, so I will invite him again. Although this is not exactly his field, but he spoke about this when he was our guest speaker. And there was another scientist who is another physicist who is exactly working on this in from University of Waterloo, who earlier, I think more than 2 years ago, spoke about this. So I will check the recording. And unfortunately, we are not able to post something written here in Clubhouse now. So probably I'll post it in my Twitter account if you would like to discuss this further and do some explorations. This
Mhm.
is my message to Electrohawk. And uh, Bob, I'd like to. There are some questions that were sent to me here, and I will pass the mic to you, Bob, after this um, question is read. Just one question. So, what are some potential avenues for extending the Alena tensor framework beyond the electromagnetic field? Are there other physical systems or phenomena for which this tensor might offer new insights or predictive power? This question came from Anne. Yeah.
Okay. Yep. Natural extension of Alena tensor is for electroweak, and this is natural. Right? Natural. I mean, it's quite easy to obtain, and of course, it needs some confirmation how it works with this field. But it's, let's say it's quite easy. It's even, I would say, natural next step. So I also refer to it in the article, in the latest article, and show how to do it. And when we will be published, even if nobody will calculate it, then we will do it, because it doesn't look like something really, really hard. But there is a much harder thing related to strong interactions, because I said they appear more like, let's say, the cousin of gravity than like classical interaction. So in our picture, it seems that this is not so easy to extend it to strong interactions. We will see. Maybe we'll calculate it. Maybe somebody other will do it. But not at that moment. I would say, uh, we would close the list of interactions because we already have gravity, we already have electromagnetism. It's quite easy to do it on electroweak, so there is only strong interaction and nothing more. So the strong interactions is a question mark, but electroweak, yes, for sure. uh, Gravity, electromagnetism, and strong force, we have some clues that it may be something different that we thought. As I said, maybe this is rather some cousin of gravity than typical interaction. We will see. Maybe I will have time to calculate it, and it will appear that I'm right, that this interaction should be treated a bit different that previously. So Alena tensor we are able to extend it to, I would say, any field. If we are able to describe any field, what any kind of field, you are able to add this Alena tensor. So yes, it may be extended to any field that we can imagine. Even we could even imagine some field and add to Alena tensor and check how it's going to behave. So it's able also this is also a tool for completely theoretical research.
Yeah, thank you. So, Kevin, you just flashed your mic.
Oh yeah, just gonna throw in because you mentioned Avi Loeb. If you didn't know, CM Huang, for homosexuality, the last speaker. He directs the research for the Galileo project. If you didn't know.
Mhm.
Yeah, okay. Yeah, so, um, Bob, would you like to take over moderation because Inar is here on stage and there
You know,
are other comments on the room
okay.
chat.
I have some information because I will have to finish in about 5 minutes, so maybe just one final question.
Yeah, so let's give it to Inar.
Yeah, hi people. Just a short question here. I got some answers already, actually. The thing is that I'm wondering if there's a possibility of the shield of the nuclei can operate in different directions simultaneously, basically. If there are any information around how they behave when it comes to the direction of the spin. Yeah, thank you.
Hmm. I'm afraid, my English maybe is not so perfect. So, and it was, quite low volume with your speech. So, if you can ask once again very exact question, maybe it will be easier for me to understand and respond.
Okay, so I'll try again. Let's say that the spin has an effect on uh, the particles, elementary particles in the nuclei, which basically is held together by the gluon. And the spin has a tendency to make these behave differently. And I was wondering if the spin can operate uh, in different directions at the same time, basically. If there are some form of shields around the nuclei, it's kind of hard to explain in short terms. Thank you.
Okay. Okay, there's now something which is called Gerlach force, and this is kind of relativistic force related to the spin in the system of particles. And we didn't calculate this exactly, but it seems that our electromagnetic potential that we have derived in natural way supports this, let's say, Gerlach description. So if you are interested in a very particular, very specified phenomena related to the behavior of the spin, I cannot answer directly because we didn't calculate some specified system. So we didn't just get the numerical, for example, solutions of the system. However, I'm already curious. I mean, maybe your question will be also part of the next research process because it's also a natural step in this research progress to calculate some system and check how the spin exactly behaves and what we are able to take from the equations. So the answer is at that moment I don't know this exact answer. Maybe it's possible to calculate it, but for sure this solution for the spin that we have already find out supports changes in spin. So probably there is some possibility to calculate it, but with one small disclaimer. A small disclaimer means uh, from our equations also shows up that we are not able to exactly predict a quantum system. Otherwise, by the way, otherwise it would be in contradiction with present knowledge. We have Heisenberg principle, so we shouldn't expect that our Alena tensor gives us the exact solution of the system showing every state of every particle in time and all so on. Yeah, so we shouldn't expect it, but we are able to, for example, make some numerical calculations, some numerical solutions showing some probability of behavior of the system in some specific moment in time. So maybe it's possible to get answer for a question. Okay, it's interesting for me. So the answer is I don't know, but I will check this.
Nice. Thank you very much. Anyways, it's yeah. Thank you
I
very
can
much,
add a
Feli.
small comment, Peter, if you want.
Yeah. Yep.
Because the question was quite technical and the answer should be a little technical. If you want to calculate something like that, then from our point of view, you will have to take a Kerr-Newman metric, do the Kerr of the composition of that kind of metric. So to have 3 plus 1 metric with 1, which is proper time that can be well understood in quantum mechanics. and then try to calculate with the Taylor theorem, the Taylor series, not the simplest one that you do in the analytic mathematics, but with the 3+1 system. Try to calculate the Lie group commutation rule and then try to figure out how the spin will act in that kind of system, for example, for two particles interacting. And this can lead you to some kind of results. Of course, you will get there also another parts that are coupled to a gravity, not only to a mass and charge, but then you will have the proper time, and you will more or less get to know how this works. It will look like more or less the classical way of quantizing the gravity, which don't work in the 50s, but here it can get some kind of results. But the calculation are quite huge if you want to interact with all of this. So this can be a real problem, especially if you are really want to have also there are gluons or something like that. So the interaction particles, because this will be another series in the Taylor series interaction of these two
Yeah,
particles. So calculation, you
yeah, a
we
lot
know
of
more or less how to do that, but to calculate this properly, it takes time and understanding what and have a proper interpretation of the results, and the interpretation is quite complicated.
yeah, yeah,
To proper
uh,
scale of the energy, you have to decide which part are look similar to the standard model particles and which part are look different, and where to find something that is interesting for you in the particle physics zoo of particles, because the standard model is a little mess.
yeah. It's kind of zone of
Oh,
particles. That's true.
this is a little too long and too complicated comment about this.
Yeah,
Thank you very much. Thank you.
Yeah, thank you so much, Peter and Peter. So I hope we will have more time and opportunity next time to do more discussions. And as I heard earlier from Peter, he said that he has to go soon. So we're going to prepare to wrap up. And yeah, I hope that we can expect next session as you try to progress in your research. And also, we'd like to thank you for the beautiful slides that was in the presentation. Probably Bob will try to collate it and put it in our YouTube channel. He had done a marvelous job of initially trying to sync slides into the conversations that we have here in Quantum Photonics in YouTube now. And pretty soon we will be opening our YouTube channel, and therefore we will be including your presentation here. So
thank you.
it is very great that you presented these very graphic slides also, because it can help the audience digest what you're trying to present. So as I prepare to wrap up, I know there are a lot of questions, but please come back next time. There's going to be a next time. So I'd like to thank both of our speakers, Peter and Peter. And if you have some last messages before we close the rooms, Peter and Peter, I'd like to pass the mic to you now.
Thank you very much for invitation, and I hope we will be able to give at least one more time, some new insight about state of research.
Thank you. And Peter, uh, can see.
Uh, well, it was nice to meet you all, guys, and nice to hear Peter and see the slides. But as you see, there's plenty of things that we can still dive in and try to figure out how this works, or try to find our approach to give the same results, but with the better understanding what happened in the standard model with this under Alena tensor and this decomposition, because then we can try reconstruct things that are put in the standard model just by hand and say, oh, this is SU2 symmetry, and this have to work like this. We can try to find the real reason for that kind of symmetry, for example. So there's plenty of things that can try to figure out here, and I hope that we will try to present more results in the future. Thank you very much.
Yes, thank you so much. So, hope to see you back here soon. And yeah, I'd like to thank everyone who asked questions and the people who are here on stage, Kevin and Einar, and earlier those who spoke on the room chat, Eagle Hawk and Kyle, maybe. And yeah, thank you so much for asking the questions. And everybody, thank you for listening. And so, I'd like to pass the mic now to Bob.
I wanted to say thank you as well as Cecile. I'm already collecting questions for the next time, so get ready. Thank you, brothers.
Yeah, all right. So we shall now give the mic to Darcel to help us close the room.
Thank you, Cecile, and thank you, Doctor, for a great, another great room, and we await your return. To close the room, we're going to start a countdown from lucky number 7. Is everybody ready?
Yep.
Ready?
Hey,
Yeah.
Enar 7,
7.
Kevin 6,
Sixers.
Bob 5,
5.
Cecile 4,
4.
I'll be 3, Tres, I'll be Dos Equis. Oh, Kevin, did I say Kevin? Did I get you, Kevin? Or I missed you?
Yes, Philly,
Okay.
Philly Sixers. Because I'm Filson.
That's right, you're 6. Okay, and I'm Dos Equis too. And Peter R. and Peter, Dr.
Oh,
Peter, you're both number 1. Call it out in unison.
One.
One.
thank you so much. Hope to see you again next time. And please check out our upcoming rooms. Bye, everyone.
Bye.
Right.